Hey sir, my name is Luis D. Montemor, and today I'm going to be talking about and running through the interpolation through the usage of MATLAB. So this is going to be a part of the machine problem number 1, which is the use of computer applications for interpolating a set of data. So this subject is ENE161, Computer Modeling Applications for Environmental Engineering and Planning, Section M5. So before we go into the discussion, we will discuss first about the highlights of this presentation. So first is that I'm going to talk about the study that's used in this activity, followed by a disclaimer. Number 3 is also the use of MATLAB in interpolation. Number 4 is going to be the discussion, and number 5 is going to be the conclusion and the answer to the question that was published in the Google Classroom. So the study used in this activity is the synthesis of 5-hydroxymethylfurfural from glucose, fructose, cellulose, and agricultural wastes over sulfur-doped peanut shell catalysts and ionic liquid. So this study is authored by Chang, Muega, Ofracio, Chen, Barte, Abarca, and De Luna. So this study was published in March 1 of 2022 in the journal named Chemosphere in their 291st volume. So I'm going to run through you about the disclaimer of this presentation. So due to the lack of numerical data shown in the paper, specifically in the figures 3a and 3b, I had to rigorously estimate the values through measuring it relative to the data plotted using the y-axis. I do not claim 100% accuracy in the data that is going to be shown here, as this is solely going to be used for demonstrational and educational purposes only. So the figures and the data used is shown here. So figures 3a and 3b respectively from the Chang et al. 2022 paper, on the HMF synthesis from biomass and agricultural wastes over SD-PSC or sulfur-doped peanut shell catalysts and ionic liquid. So for this one, PSC1, which is in figure A, 3A is the usage of the peanut shell catalysts that were doped in sulfur for an hour, and this one on 3B is PSC5, which is a peanut shells doped in sulfur for 5 hours. So for data set number 1, which is going to be the Lagrange piecewise linear and the cubic spline interpolation, so this is going to be overlaid using MATLAB. So the table title is the plot of the 150C parameter from figure 3A of the PSC1 or 1 hour dope sample. So we have our values T and Y over here. So T represents the time in minutes, the reaction time, and Y is the amount of production in weight percent of 5-HMF or hydroxymethylfurfural. So before setting up the code, all of the work is done through MATLAB, which is a multi-paradigm programming language. So the specific build of the MATLAB that I used is R2022B, which is released in the second week of September, so around 2 weeks ago. So here's the code. Setting up here is we wrote CLC semicolon clear semicolon, and then followed by the values of T and Y, and then we add the %n as the number of points, and we assign the n as length T, and then for the Lagrange polynomial at 5th degree, since we have 6 data points over here, we attach a for loop for this one. Then P is equivalent to sum of X, and F is equivalent to flip of P, and then we display in the command line the resulting equation of this one. So for k is equals to n is equivalent to -1 is equal to 2. Then we fprintf the following equation, and then we end it also with another fprintf. For percent Lagrange interpolation, t is equivalent to length space t of 1, then t of n, and then 100, and then y polyval t comma t. Then the cubic spline is set up the same way in the following slide. So tt is equivalent to length space t of 1, t of n, and 100, then cs2 spline t comma y comma double t semicolon percent normal way. So for the piecewise linear interpolation, it's assigned by lin is equivalent to interp 1, then t comma y comma t, and then open close quotes linear, then close it, and then we put a semicolon. For the plots, over here we can see that plot t and y and ko, and then big T and big Y and M. So for M, this is the color that's going to be assigned, where M is magenta. Then TT and CS2, this is going to be the cubic spline, which is assigned the color blue, and then the T and the lin, which is assigned to the linear interpolation, is assigned the color red, and we close this one. So for the Y label in the plot, we put the HMF field in weight percent, which corresponds to figures 3a and 3b, and then the X label, time in minutes, which corresponds also to figures 3 and b in the original study. So we put hold on and then the grid on. So the grid on is for in order for the grid to be shown upon running it. So here you can see the legends. So for the legend, data points, then Lagrange polynomial, then cubic spline, and then the piecewise linear. So at the end of the liner here, we put ENE161 machine problem 1, then the title of the study and the author, and then we close it we close this one and we run the program. After running the program, we are given this plot, which is shown in a different window. So as you can see here, in the legend, you can see that the piecewise linear function of the plot is just a straight line, and then the cubic spline is a curve, which is indicated in the blue. You can see here, and then it goes all the way up. And for the Lagrange polynomial, it's kind of the same way as cubic spline, but there are differences as the cubic spline actually uses all of the usable data in order to create this plot. So part 2. So I did a separate cubic spline interpolation so that I would be able to see any if there are any differences, or let's say I would only like to see a certain visualization. So for the tables, dataset 2 for a separate cubic spline demonstration. So the title of these tables are comparing the splines of the 140 degrees Celsius parameter from PSC1 and PSC5 samples. So PSC1, as what I mentioned earlier, is peanut shell catalysts doped for 1 hour, and then peanut shell catalysts -5 are doped in 5 hours. So same setup as earlier. T is the reaction time in minutes, and Y is assigned to the 5 HMF production, which is in weight percent. So for PSC1 at 140 degrees Celsius, it starts with CLC and then clear, and then you can see here the data and the six data points that we are using for PSC1. So percent %n is the number of points, same as earlier. Percent %n is length of x instead of the other parameter earlier. Percent cubic spline is also set the same way earlier, where x is equivalent to length space 0.00, x of n, and then 100, and then cs1 spline xt double x semicolon, and then plot xt koxx cs1. So this is the cubic spline, and then assign the color magenta, and then we add a line width, which is a value of 1.5. So for the x, the limit of the x is from 0 to 150, so that we would be able to show at the x-axis the values from 0 to 150. And then the y limit is equivalent to 0 and 4, which corresponds here to the values of 0 to 3.9. The y label, it's indicated as HMF yield in weight percent, and then x label time in minutes. So hold on, and then grid on, then points, then PSC1 at 140C, location, and then test. And the legend is boxed off. So the title for this one is a cubic spline of 5 HMF synthesis in PSC1 at 140 degrees Celsius. For PSC5 is set in the same way, except that we only interchange the values of the array, and then most of this here are more or less the same except for the title. So the resulting plots after running the program are these two. So for PSC1, which is indicated in red, shows a kind of a very fast increase and then a slow increase at around 90 minutes. Over here, you can see that there's also a sharp increase at 30 minutes for PSC5, and then it slowly decreases and it increases and it decreases again. So this is the cubic spline for PSC1. This is a clerical error, and then the cubic spline of PSC5 at 140 degrees Celsius, both of these. So now, I was able to overlay these two plots together, and I did not actually see that at the 90-minute mark they had the same value at 3.4. So the cubic spline of 5 HMF field against reaction time. So at 140 degrees Celsius, PSC1 is in red, and then PSC5 is equals to blue. And now we ask the important question: which interpolant gives more reasonable values between data points, and why? So my answer is that in some cases, it is known that the cubic spline is more reliable and gives more reasonable values in between points without the use of a calibration curve. So the cubic spline can also become unreliable, especially if the gap between the points is vast or big, and that is where the Lagrange interpolation can be used. So yes, in some cases the Lagrange interpolation is more favorable over than the cubic spline. However, in this case, the cubic spline has shown more reliability and consistency in the values, given that there is no significant oscillation in the curves between the values. So this wraps up my report for machine problem number 1. Thank you so much for listening, and may you have a good day. Thank you so much.